I think with artificial intelligence, the computer would know what I need, right? And it would does whatever. Anyway, here we go. Okay, objective. Remember the talk that we talk about, the introduction? It's here. Let's see to introduce the equivalent or the work equivalent method for replacing distributed load by a set of discrete loads. That is the equivalent nodal forces. Okay. For distributed load, you will go to fixed end moment. What about if you have sine or if you have some funny? You have a formula. We will derive that formula. How you find the forces at the end and the moment. Then we'll introduce the general formulation of solving a problem. The general formulation is here. K for each element, a symbol, find this, and that's it. It's here. That's the general. You see how much we save time by discussing things? Okay, then to analyze the beam and distributed load acting on them, yes, you'll apply it. And then to compare finite element to exact solution. So hopefully we can finish this before the time. Okay? Okay, let's see. I think I need to use pointer. What is this? Distributed load. Okay, anybody will tell me what are those forces here?
The equivalent.
Is this the equivalent nodal forces? No. This is called fix and reaction. It's not equivalent because they are opposite to the load. So if somebody asks you, if somebody give you this, and he said, what would be the equivalent nodal forces? It would be what? Equivalent nodal forces will be opposite to the fixed end. So this force will be down, this force will be this way, this force will be down, and so on, okay? So it's just opposite. Okay, so do we have tables for the fixed end moment?
Yeah.
Okay. Yes, look at this. Now, if you want to make this load distributed to node 2 and node 3, what you are going to do? 2 steps. You will find the equivalent nodal forces, which is this one, and then you will do what? Reverse them. You can see that the load is upward. Reverse them, they should be what? Downward. Look, they are downward. Here, look, opposite. Okay, what about if I give you, if this is for, if I use this is as one element, what about if I want to use 2 elements? You will apply the same method, even if you have here node. You choose this as what? You fix this, and you fix this. And then you find the fixed end moment for this, you find the fixed end moment for this, and for this node, which is common to this and this, you add them together, right? You know it already. So this is what happened. Like this one here, and this one is coming in the left node. Okay, what about the right node? The right node will be this and that. Okay, what about the second element, the left node? It will be this and that. And the right node will be this and this. So you can see that the middle node will have contribution from element number 1 from the right and contribution from the left, right? This idea of equivalent nodal forces, what is it about? Very, very simple. You equate the work done by the distributed load to the work done by the equivalent nodal forces. Any 2 systems are equal if they produce the same work. So the work done by the distributed load should be equal to the work done by the concentrated load and concentrated moment. Very simple. So you can see the first formula is what? The external work done by the distributed load. Okay, those who doesn't know from where this formula came, right? Is it easy? The first formula here, 1, 2. One is distributed load, the other one is concentrated loads, right? Think this, 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 and this. This one we call it what? F1Y. This one we call it M1. This one we call it M2. This one we call it F2Y. Then with this, it has what? What's the displacement we call it? We call it V1. Phi1, V2, Phi2. What would be the work done when it is concentrated? You just multiply this times that, this times that, this times this, and this times that. That's it. This is the work done of the equivalent nodal forces. Now, what about the work done by the distributed load? You have to choose an element, you see, and this is a distance dx, and this is the height of the load, which is w. So how much the total load? It will be like this. This one here is the deflection. So how much the work done due to this element? It will be the load, which is w times dx times the deflection. This is the work done on this element. How do you find the work done? Integrate. That's it. That's what you see there. W deflection dx from 0 to L. That's the work done by the distributed load equal the work done by equivalent nodal forces. Force times displacement, moment times rotation. You equate them, okay?
We solve for what?
Yeah, we're solving for what?
The unknown.
The unknown. This F1y, M1, M2, F2y, equivalent nodal forces. Okay, do you remember this table? Now, what is this? Is this equivalent nodal forces or fixed in moment? Tell me. Huh? Is it equivalent or? Okay, just simple. This load is down. The reaction should be up, and the reaction here should be up, right? So reverse it. It will be down, down. So it's minus and minus. So this is equivalent nodal forces. We took it from fixed moment and we just put minus sign. That's all. We reverse it. Okay? Very simple, right? Okay. Now, what is this? This is the one on the board. That's exactly the one I explained. This is the distributed force. This is the equivalent nodal forces. You have to equate the work done by the distributed load to the work done by the equivalent nodal forces. Okay, I think you like this slide. The work done by DL, distributed load, equal the work done by the concentrated load. Okay, now in order to integrate, you have to put V in terms of the shape function. What is V? V is N1 V1 plus N2 Phi1 plus N3 V2. You see, this is from here to here is nothing but what? V, right? Yes, right? What is your friend? Still he's sick? Huh? I didn't know your friend. He's sick? Oh, so he may drop the course, right? I think he will drop the semester, right? Okay, we'll work together. Okay, so this is here, from here to here is V, and this is the load, and this is dx. Okay, and the other side, F1y. Okay, now when you integrate, what is N1? N1 is function of x. You can integrate it. N2 is function of x. N3 function. V1, Phi1, V2. Phi2 is not function of x. So from here, can you tell me what would be F1y? F1y. Anything multiplied by V1 is F1y. Anything multiplied by Phi1 is M1. You see? So when you integrate this, what did we do? We just separate this to 4 terms. 1, 2, 3, 4. 4 terms. And the right-hand side equal to this. So this is the left-hand side, and this is the right-hand side. These two are equal when this one is equal to that. When this equal to this. Is that right?
Yeah, right.
So we have how many formulas? 4 formulas. Now that's it. I can give you now any load. You can tell me what would be F1y, what would be M1, F1y, F2y, and M2. Why? Because you just take this shape function, you substitute, and you integrate. Straightforward. And the shape function is easy. Only x squared over It's very easy, right? Okay. Did you see this equation before? Wow, yeah. See, it's nice to see it again, right? Very nice. So F here is the reaction. K, D, and F naught is what? Equivalent nodal forces. Okay, let's see. What is this? This is the distributed load acting over the beam when you have fixed end moment, okay? And then you can find it, okay? This is what happened when you have cantilever. So if you have cantilever, okay, let's do it for cantilever. If you understand it for cantilever, I think you can do the rest. Okay, can you tell me the procedure? Cantilever with length L with uniform load W. How do you solve it using this method? With one element. Okay, cantilever. Okay, cantilever. Uniform load. W, L. Node 1, node 2, element 1. Procedure. Procedure means what? Reaction or F equal to K D minus F naught. Okay, so first thing, what is F naught? Can you find F naught? F naught means you fix here and you fix here and you find. So you can find this one. Okay, do you know K? Yeah. You have closed form 4 by 4. You know K for the beam. If you know the area, if you know the A. Okay. Okay, what else? Do you know the reaction? Okay, let's expand now. Okay, tell me, what is the reaction? F, capital F, 1. Okay, then, do you have moment? No, not 5. Moment, forces, right? M1. Okay, what else here? Huh? 0, 0. Because the other end, they don't have support. They don't have reaction. No, I'm substituting here. 0, 0 equals 4 by 4. You already know it. Okay, these. Yalla, tell me. 0. 0. What is this? V2 and V2 minus. And here, what would be?
0, 0.
Huh? What is everything 0, 0? Equivalent nodal forces. Wow, mindfulness, right? 0, 0 or what? Okay, tell me. Yalla, structure analysis. What is this? Tell me the fixed end moment. Yalla, if you have fixed here and fixed here, I think you should know W and this is L. The reaction here will be W L over 2, and here the reaction will be W L over 2, and the moment here will be what? W L square over 12, and here W L square over 12. This is not the equivalent. Reverse them. Now, do you know the sign convention? Here, what do you think you need to put? You have to reverse this. If you reverse, it will be down. It will be minus W L over 2. What about the moment? Is it minus? Yes, minus W L square over 12. Okay, here. Is it minus? Minus W L over 2. What's the other one? Also, positive or negative? Yeah, positive, because you have to reverse it. It is negative this way, but when you reverse, it's counterclockwise. So it will be positive W L square over 12.
That means the first one would be, the second one would be what?
So how will you solve this? I think you need to solve for what? The first thing.
For the unknown.
What are the unknown?
Yes.
The primary unknown, V2 and V2. And then you substitute here, and then you find F and M. Straightforward, right? That's what he did. Okay. Let's see. Oh, do you see this? Is it the same? The one on the board? Okay. This is the effective. By the way, they consider K times D as F effective. So they multiply this by that. Once you know V2 and C2, then you can call this is as F effective. And F effective equals to the reaction plus. So you move this to there. This is the other way to look at it. Okay? Because once you solve for the primary unknown, you could find K times what? K times what? K times D, right? K times D. And then you can take the F naught to the other side plus F naught. This is called FE. See? F effective. Okay? What is F effective? You see F effective? You see F effective? It's K times what? K times D, right? So F effective. Now you want to find the reaction. How do you find the reaction? How do you find the reaction? If you know F effective. If you know F effective, you multiply K times D. How can you find the reaction? It is F effective, what? Minus F naught, right? This is the reaction. So this is how it is done, okay? Systematic. Okay, now tell me, is this a good problem? Can we do this? Don't tell me that you need to take a node there under the load. You can solve this problem without taking a node under the load. You just have to fix this end here, right? The two ends. You fix this one and you fix this one. And you get the fixed end moment and the fixed reaction, and then you reverse it. Do you think this is fixed end moment or equivalent nodal forces? Equivalent, because in the same direction, right? This is F naught. That's it. You just find K. Do you know K for the beam? Yes. Okay, and then you put the reactions and everything, and you can find these two unknown, which is the free end, V2 and P2, and then you can find F effective. You see F effective? Yeah. K times D. And then after that, how can you find the reaction? Osama, how can you find the reaction? Reverse it? No. This is K and this is D. We multiply K times D, we get F effective. It's here. I said, how can we find the reaction? To find the reaction, you have to take this product and you subtract from it the equivalent nodal forces. Let us see in the next step. Yes, you see the minus sign? This is F effective minus the equivalent nodal forces, and that will be the reaction. Look at the reaction at the free end, 0, 0, because there is no support. And you have only this one here. How can you do it? Triangle. It's nothing, right? You just go to the table, find the fixed end moment, reverse it. That is F naught. Straightforward. Once you understand that there are 1, 2, 3, 4, that's it. Only 4 things. 1, 2, 3, 4. And you need to start with F naught. Okay. Yes. What happened here? It looks like he's using two elements, right? Here using 2 elements. Okay. Okay. So what you need to do? This is fixed support. This is fixed support. You come in the middle and you make it fixed support. You make it fixed support for the element on the left, and you make fixed support for the element on the right. You see? And then you find the fixed end moment. Now this, you put it here. This, you put it here. What about the center? You have to add this to this. You see it's minus W. How much this? Minus WL over 2. Is it? Huh? Huh? Sine law? What did you say? I don't understand. ايش قاعدين نسوي؟ قاعدين we distribute it to the ايوه مركزه مداير. ايوه انا مش حجاوب على السؤال هذا، الشباب حيجاوبون. If we have load applied at the joint, what do we do? Keep it as it is? Yeah, you keep it as it is, right? Nodal forces. There is no distributed load. There is no distributed load. ما في equivalent nodal forces. في concentrated force. يعني هذا بدل triangle I give you only load here. We can divide it. No, this is already equivalent nodal forces. If I give you load P here, why do you divide it? It's already given. Only for the distributed load you see the contribution. But if there is load here, concentrated load and concentrated moment, your life is so easy. It's there, right? Huh? I'm talking about if it is two elements. Yeah, two elements. He's talking about when it is two elements. But if it is one element, definitely you have to throw them to the side, right? Here it is two elements. That's what I'm talking about. And that's what you are not realizing. Okay, this is two elements, not one element. Element L from here to here. Element 2 from here to here. So here, the element number 1, you use triangle. For element number 2, you use trapezoidal. You see? Look at it. This is triangle. This is trapezoid. And then you add those together and you get it. Okay, this is K1, this is K2. And then you find the primary unknown is what? V2 and Phi2, right? What is it? What is V2 and Phi2? The center node, right? Because V1, Phi1 is 0. V2 and Phi2 is unknown. V3 and Phi3 is 0. So your unknown here is 2, and that's it. And then you can find the rest. Okay, look, the effective. How do you find the reaction? Reaction will be F effective minus the equivalent nodal forces. Okay, let's see. We got 0, 0 here. Why you get here 0, 0? We got if because there is no reaction, right? Node 2, there is no support at node 2. We have only support at left 1 and at 3, right? Comparison with finite element. Okay, now we are comparing finite element with the exact solution. If somebody give you this and he asks you what would be the exact solution. Exact solution means what would be the exact deflection and what would be the exact rotation and what would be the exact moment and what would be the exact shear. Yalla. How do you find it? Yes. Find the equation of W is uniform, constant. Huh? And find moment and reaction. And then after you find the reaction, I want deflection. I don't want reaction. I want deflection. How? No, there is a formula, EI, right? M equal M over EI equals second derivative of the deflection. You just have to integrate, right? Double integral, right? You have this from CE to O3. The second derivative equal M over EI. You just need to find moment as a function of X and integrate. Okay, then you will get what? This. How do you find the deflection? You integrate twice and you put boundary condition. Then you'll find V as a function of X and you will find V prime as a function of X. So you know the slope and you know this. That's it. Okay, how do you find moment and shear? How do you find the moment and shear? So already you have the moment here, okay? Yes. Huh? This is it. Talking about plates now, shells. They are bringing plate and shell here, right? Sign convention there is different. Okay, says we will now compare the finite element solution to the exact classical beam theory. Of course, here we are not considering the shear deformation. We only consider what? Bending. Okay, very good. So this formula. So the first thing here, we need to derive the moment. Okay, how do we derive the moment? We make a cut. We find the shear as a function of x. We find the moment as a function of x. Okay? How do? You find the reaction. This is the reaction, and you make a cut at a distance x. Summation of Φ equal to 0, you find V. Summation of moment, you can find M. Now, what do you do with this moment? You put it here, right? You put it here. Okay, you put it where? You put it here. Okay, clear. You take this moment here and you put it here, and then you'll have the second derivative of the deflection. Then you integrate it twice. Yes, we put the moment. We integrate once, we get one constant. We integrate another, we get the other constant. How do you evaluate these two constants? The deflection at x equal to 0, 0, and the slope at x equal to 0, 0, right? Cantilever. Find C1 and C2. Put them back. You find the deflection and you find the slope. Okay, how you compare this result with the finite element? It says using the numerical method, we obtain the slope and the displacement at the fixed end, Phi2 and V2. How did we get this? Can you tell me? For node 2. Already, this is we solve for V2 and Phi2, which is what? Which is the middle node. Again, I have to come here, right? Where is it? Is it this one here? Yeah. Look at the center here. We use this as two elements, okay? How much x? You put L equal to 100. So this is at the free end, right? So this is the free end because the length here is 100. So when you put L is equal to 100, you get the deflection and the slope at the free end. Okay. Now this is equation 4.4. This is finite element. Okay, what about here? How do you put x equal to 100? Let's see the deflection and the slope. Is this the finite element? Is this the finite element or the exact? Huh? This is finite element? No, put x equal to 100 here. Right? It will give you this, right? Is this finite element?
Just put L instead of X.
So you are sure this is the finite element? Huh? What? This is the analytical. Analytical is here. When you substitute x with L, you get this, right? So all of this will be collapsed to one term. And all of this will collapse to one term. So you can see y is equal V2 and y prime is equal to Phi2. So this is the closed form solution. This is the exact solution. Now, how do you do it in finite element? You already know the deflection. V equal N1 times V1, which is 0. N2 times Phi1, 0. N3 times V2 plus N4 Phi2. Okay, how do you find the deflection at x equal to 100? You just put 100 here, okay? Right? So the deflection here, this is at node 2, and this is at node 2. So this is V as a function of x. So you can put x equal to 50, and you can put here, you get the deflection. So did we understand it or not? Not exactly. This equation is what? Where is V1? Where is Phi1? V1, 0. Phi1, 0, because it's the left support. The right support then will be N3, right? And this is N4. Okay, then. So where the boundary condition, V1, Phi1 is 0. Using the numerical value of that we obtained here, we put them back in here. This one here and this one here. So how much the deflection? At x equal to, so we are taking the nodal values of the displacement and we are calculating the displacement at x equal to 50. Yeah. You don't tell me if I give you from finite element, V1 equal to 0, V1 equal to 0, and I give you V2, and I give you V2 here. And I told you what would be the deflection and the slope at x equal to 50. Then you have to use the general formula. What is V as a function of x? Using finite element, summation of Ni phi, right? That's it. And you will see that you will have what? N1 phi1 plus. But N1 is function of x. You see? N1 is function of x times phi1, right? Times V1 plus. Help me. Plus N2 function of x phi1 0 0. Continue. Plus N3 V3. But N3 is function of x. That's why you can find the slope you can find the deflection at any point in terms of the nodal displacement. Don't say that finite element is not good because it's only given us the value at the node. No. Due to the shape function, you can find the displacement and the slope at any point. Okay, very good. So he found here the deflection and the slope, and then he did this, and this is the result. Look at the result. It says here finite element. Do you think this is good? Look. This is the finite element, and this is only using 2 elements, 1, right? And look at it. Good result, right? That's what they do in the research. They show only good result. They don't show bad result, right? Now, what you will ask is, what is about the stresses? What about the moment? What about the shear? Don't say, wow, very impressive. Wallah, we got good result between theory and this, and you'll be happy. Let's complete the story, okay? Let's see complete the story. What is this? What is this? This is the moment. Look at the departure between the beam and the finite element. You see the difference? Now start the departure. The result is not as close when it comes to deflection, because the moment is the second derivative of the deflection. Maybe it is good when you talk about deflection, but when you talk about higher order terms, they are not coinciding. Okay, now, and this is what happened to those who are taking plate and shell. In the plate and shell, I think you are talking with fourth order differential equation. So this is what it is. Maybe deflection is good, but go to the other higher order term to find out. And this is what moment. What do you think the shear? Do you think the shear also will have different answer? The shear is the worst. Shear is the worst. Finite element is saying that shear is constant. Whereas finite element, the beam theory, it's here. This is, I cannot take it. So it means 1 element, 2 elements is not good. You have to go to higher order term so that you will have this to be in a state. At least you will have steps, right? Like this, like that, and then it's matching with the linear.
What we want. We want the deflection only. So, okay,
do you think life will survive with deflection?
We want here we can to save the computation time.
No, if you talk about structure, shear is important, right? When you talk about structure, you cannot avoid shear, you cannot avoid moment, you cannot avoid this. Okay. That's it. I thought that I will go to the second presentation. Okay, I can give you introduction. Okay, 5 minutes, I'll give you introduction. Okay. Do you know what's the introduction? It's about finding the stiffness using potential energy. That's it. Can you tell me how can I find the stiffness using the potential energy? I talk about it in the beginning of the class. How do you find it? External energy. That will give you equivalent nodal forces. Yes. الباي الكبيرة. Okay. It's here. A and B transpose DB We said, this is your cake. We're talking in the beginning of this. Why? I want to see how much it gets into your brain. You should tell me, we know the shape function. We just take the derivative of the shape function and we put it in column. We take D as E. B is rho. AL, multiply them together. That's it. You will get the same stiffness. EI, you'll get 4 by 4. Because how many shape function? 4 shape function. So this one will be what? 4 by 1 times E times 1 by 4. So you can see it will be 4 by 4. Now you understand the whole story. This is why when you know it for the truss, you will know it for the beam, you will know it for everything, okay? Now, what do you think next class we'll talk about, other than the stiffness using potential? Huh? Galerkin method. Okay, this is probably yes, Galerkin method. What else? If we say, okay, Galerkin, khalas, forget about it. You know, read the stiffness. Just move to something else. Inclined frame, because this beam, see, beam is only, you're talking like spring, only in one line. What about if I give you frame and inclined member? Oh, you need to take the stiffness, you transform it from local to global. Always, it's good to know the roadmap. What is next? What is next? So that you understand, you appreciate. Okay. I guess with that, we finished the class for today. Thank you. Thank you. Okay, we'll stop the recording now. Pause recording or stop recording.